So today's lesson will be on the forces that are acting on electrical currents. The picture we see in the slide is of probably the greatest experimental physicist in human history, Michael Faraday, and he did all the work around the relationship between electricity and magnetism. So today's lesson will focus around the motor effect and what happens to magnetic fields when they interact with electrical current. So when you have a conductor, say a conducting metallic wire, and it's carrying an electrical current, and you place it within a magnetic field, as we do here, then it may experience a force. Okay, so it moves out of the magnetic field. This is known as the motor effect. Essentially, when a wire in a magnetic field carries a current, the current experiences a force, and this force is a result of the fact that the current has its own magnetic field which interacts with the magnetic field externally. Okay, so it begins to move. Okay, so this force increases in three different ways. If the strength of the magnetic field B is increased, if the current I is increased, and finally if the length L of the wire which is in the magnetic field is increased. The direction of the force is reversed if either the direction of the current flowing through the wire changes or the direction of the external magnetic field is reversed, so it goes from north to south or to south to north. The conducting wire will not experience a force if it is parallel to the magnetic field, because there's actually going to be no change in the magnetic field as it moves up and down. This change is important to understanding the principle. Okay, so how do we calculate this force that the wire is undergoing when current is passing through it inside a magnetic field? Well, if the magnetic field is at right angles to the current, the force of the current is given by F equals Bill, or F equals B times I times L, where B is the strength of the magnetic field, and it's given in the units of Teslas. I is the current in the wire, and it is given in the units of amps, which we've gone through previously in other lessons. And L is the length of the wire in the magnetic field in meters, M. Now it's important to note that it's the wire which is actually inside the external magnetic field that we're considering, not the entire length of the wire. So in order to work out the direction of the force that's interacting with the current in the wire and in the external magnetic field, we use something called the right-hand slap rule, where the direction of the current is the thumb of the right hand, the direction of the force which is being exerted on that wire when current is passing through is the palm, direction of the palm, and the field strength is the direction of the fingers. Two important provisos are: one, the magnetic field is from north to south, and two, the current direction is from plus to minus. Right, so what directions are the forces going to be? Okay, so we're going to look at the first question to begin with. So the first thing we do is, what's the direction of the current? It's across, so it must be going into the page. That's the direction of the thumb. Okay, the thumb must be pointing into the page like this. Okay, there's a bit of contortionism involved. The magnetic field is going from north to south. Okay, so looking at that, the force must be going down. Okay, that's the direction of the palm. And let's see if we're correct. Okay, remembering of course that dot means the current is out of the page and cross means the current is in the page. Right, down, so we're right. Okay, so the next question asks is, what is the direction current? Okay, so again we read our right hand out. We can clearly see that it's going from north to south. The force is going down, so the current must be coming out of the page. It must be a dot. That's correct. The north and south poles. Okay, well, if you look at question 1, the north and south poles are there and it is going up. So we know that the direction of the current is coming out of the page. It's going from north to south. Okay, so wings this way. Okay, it's a bit of contortion. So that means it must be going up. Okay, so that means the direction must be going of the magnetic field must be going from my left to my right. And that's definitely what we see. And the directions of the forces in the final examples, there's 2 examples, and we can deduce that from question 1, then this guy must be going down, and this guy must be going up from question 1 and question 3. Let's see if we're correct. Indeed, we are correct. Okay, so a bit of contortioning of the body, but we get there in the end using the right-hand slap rule. So a clear example of the power of the motor effect is in the DC or direct current electric motor. So electric current flows around this coil of the electric motor and produces oppositely directed forces, as you can see from the diagram. The reason being, of course, is that the current is in opposite directions on each side of the coil. These forces cause the coil to obviously rotate because you've got 2 equal and opposite forces, one force acting down, one force acting up on each side of the coil. So one side goes up, one side goes down. Every half revolution, the split ring commutator causes the current in the coil to reverse, otherwise the coil would stick in the opposite direction. Okay, because it arrives at a position where there's no current flowing in the coil because it's parallel to each other. However, if the forces are opposing this motion, a small coil continues to rotate this past this vertical position due to essentially inertia. Okay, object in motion will want to stay in motion. Bit of Newton's first law. Okay. So these brushes, the way the commutator works is that the brushes are in contact with the split ring commutator. Okay, these contact brushes here. The current flows through the metal coil or motor coil, and forces exert a clockwise turning effect on the coil. Okay, so this is kind of an animation there, so let's go back slightly, there you go. So the coil will continue to rotate clockwise due to the momentum, or due to inertia as well, the fact that an object in motion wishes to stay in motion. Okay, the brushes regain contact with the split ring commutator and the current flows through the motor coil, but this time in the opposite direction. The forces then exert the clockwise turning effect on the coil. Okay, and then it goes back to its new position, as you can see from the diagram. Again, in the completely vertical stage, the brushes lose contact with the split ring commutator. Current no longer flows through the motor coil. But again, the coil will continue to rotate clockwise due to the fact that it has momentum. Okay, it wants to keep on moving because it takes an external force to stop that movement. And again, we continue on, and it goes on again. And that's just a diagram of a model electric motor, which we have in the science department, and maybe your physics teacher will get it out and have a look at it and see how it works. Okay, so as a final example, and introducing the concept of alternating current in magnetic fields, which we'll look at in more detail in the next lesson, let's look at the loudspeaker. So in a loudspeaker, what happens is that when a current flows through the coil, the magnet exerts a force on it. This force makes the cone move. Okay, as you can see there, it causes vibration. When the cone moves, the air next to it must also move, and this produces sound waves which vibrate in step with the original sound signal. If the current keeps changing, alternating, then the force on the cone will keep changing and the cone will vibrate. This causes the air to vibrate as well, and this vibration in the air, we hear as sound. Okay, so the diaphragm, this black part here, causes the air to vibrate and creates a sound wave so we can actually hear the music. Okay, so the next lesson will be on, this time, the forces not on a stationary wire, but on actually a moving wire. or moving charges, and how we induce current. And how this is very useful when we are creating AC, and also looking at other more complex problems when it comes around with electromagnetism.